tell you, give me the type of symmetry that you are breaking, give me the dimensionality of the order parameter space, and we can classify all these defects, okay? And of course, the dynamics and the stability of the defects depends a lot on the dimension. Here I made an example. So if you make a hole, like a point defect in 2 dimensions, you can see that if you take a loop around, you cannot shrink it, okay? There's no way that you can shrink it. So this is if you want stable defects in 2 dimensions. But now if you go to the same situation and you just make a hole in 3 dimensions, you can easily take the loop, pull it out, and close it. So this means that in 3 dimensions, that topological defect is not stable, okay? Because you can always unwrap something about it. This is not the case for a string. For example, a string in 3 dimensions, you cannot do that because whenever you are outside, you can never connect it continuously to something that is not this hole in the middle, okay? Now, apart from the math, today we're discussing physics. So the question is, why do we care? Okay, why I'm here discussing with you defects? Well, one of the reasons that we care is linked to a very simple problem, which is take whatever crystal, take your form, break it, and try to guess or to derive from physical laws when it will break. I mean, which kind of stress you need to apply to break it. So if you assume elasticity theory, you can do a computation, that's what's actually done, and you find an expression, okay? Now, you do the 3 orders of magnitude before what you expect, okay? And then there is the question, what is happening? Because it's not a factor of 2, it's not a factor of pi, it's 3 orders of magnitude. And the answer was actually given by Frankel in his very famous work. And the idea is that there's no crystals that has no defects. So there is no ideal crystal. Whatever crystal has always inside defects, and these defects are the responsible for the fact that this breaks before what you expect from elasticity theory. And from a mathematical point of view, there were 3 famous works in the same year, 1934, that identify what these defects are, using also notions that were already discussed by people doing geometry, okay? So Volterra, Weingarten, etc. So type of defects in crystals. So little summary. So there are 2 types of line defects in crystals that are topological. They are called dislocations and disclinations. A few properties of these defects. So first of all, you can observe them through direct imaging. And on the top right, you see one of these examples where you can directly see these defects. Again, important thing, these are necessarily to explain why these crystals break so easily compared to elasticity theory. And from a theory point of view, you can define these defects from topological numbers. So these topological numbers we will see in a second are called the Burgers vector and the Frank vector. And also importantly, they are connected to geometry. So for those of you who works in gravity, you will see that there is a nice description of these topological defects in terms of gravitational objects like torsion and curvature. Now, from a more dynamical point of view, these defects are responsible for plasticity. So what is plasticity? Plasticity, by definition, with my definition at least, is irreversible deformation. So you do a deformation. If this object is elastic, let's imagine I pull this wire, I will pull it, it will go back. That's an elastic deformation. If I pull it too much, it might be that this elastic band does not go back to its original shape. This is an irreversible deformation, and this is linked to plasticity, okay? And it's well known, especially to engineers, that plasticity in crystals is driven by the dynamics of these topological defects, in particular this dislocation. So if you want, in a sentence, what you can say is that these topological defects are the carriers of plasticity in crystals. And here, if I manage to run this, you can see how this little, how this little dislocation is basically moving around. Okay, so this object can move around when you apply deformations, and those are the responsible of the slip and the breaking of the crystal. Oops, now how I do it. Okay, so the first type of topological defect is a dislocation. So what is the dislocation? So here you can see 2 examples. There are 2 examples. One is called an edge dislocation and one is a screw dislocations. So the idea is that you take basically a crystal and you take a plane and you basically slip it around of a vector. Okay, so this vector mathematically is called the Burgers vector. It's a topological invariant, and it can be found by integrating over a closed loop the displacement. Okay, the displacement of this particle. Now, From the theory point of view, this is equivalent, for those of you who know this expression, to the violation of compatibility. So the violation of compatibility means that your deformation can be not anymore represented by in a compatible way, and therefore the relation between the strain tensor and the displacement is not one-to-one anymore. Okay. From a point of view of geometry, the appearance of dislocation is linked to torsion. Okay, so you can map elasticity into a geometrical theory with a metric by basically taking the point of view that instead of being the atoms in the crystal moving, is the geometry in which these atoms are embedded that is deforming. And if you do so, you can derive that torsion is the responsible for this dislocation. Indeed, torsion is the density of these dislocations. And here you can see clearly, integrating this density, you get exactly the charge, which is the Berger vector. Now, disclinations. Disclinations are another type of topological defects, and the simplest way to understand a disclination is as follows. Imagine it's your birthday, you have a cake, you cut a piece of the cake because you're hungry before the birthday, but then you don't want to show to your friends and you close it again. Okay, so you will create a topological defect in this case, which is the cake is now missing an angle. Okay, so that's exactly what this represents. So you take basically a circle, you cut a piece, and then you close it. Okay. Now, if you are forced to be in 2 dimensions, you will create definitely a topological defect that, in principle, if you go to 3 dimensions, can be released by curvature. So the simplest thing, something like this. Okay. So you can basically cut it. If you cut it and then you close it, you will create a tip in 3 dimensions. Okay. So this tip will be associated with a curvature. And that's exactly what this expression here is telling you. So these kind of defects, these are rotational defects. They are defects related to angles. And they are source of curvature. Now, again, to make an example, this is a simple example. Imagine you have a 2-dimensional material with an hexagonal lattice. So in principle, if it's a perfect crystal, each of your friends, you have 6 neighbors. Okay. Now, imagine you cut a piece or you remove a piece. Okay, so what you will find out, and that's what basically this figure is showing you, is that you will end up with a place where instead of 6, you have either 7 or 5, depending if you remove or if you add an angle. Okay, so this guy here is a disclination in the microscopic sense in this hexagonal lattice. Okay. Now, this was a bit like a quick introduction to topological defects in crystals. So it's a good moment if you have a question. Otherwise, let me move to a situation which is more complicated. Of course.
In the previous case, in the last slide here, why you call that a topological defect? 7 ring and 5 ring, this defect seems very local.
No, so that's a good question. So local topological means that you cannot remove it with a continuous local transformation. So what you can convince yourself, and that's basically this kind of picture, that you can remove so you cannot just remove one of these because you need to cut an atom, you need to cut a bond. So the only way is that you remove it by doing exactly this feature. So you need to cut a full piece, and then you will remove the 7 and you go back to 6. But this, of course, is not an operation which is continuous. You are cutting. So this is very different. For example, this is a good question. Let me maybe go back to the initial slide. So here, if I have that, can I remove it with a continuous transformation? Yes, I just compress the solid. It will become a solid with a crystal, which is a smaller lattice spacing, but I can definitely do it. If I have this, can I remove that? No, I need to remove a complete line of atoms. So I need to take an operation of the full system and cut out a full line. There's no way you can think. You can move these things, of course, but you cannot remove it. While this can be removed. So that's basically the difference between topologically protected and not topologically protected, if you want.
Also, when you show the defect, you call it the instanton.
Instanton? No, I never use that word. So I will not call it. This is just a dislocation that is moving, is sliding in the system. You mean this one? So this one is usually called the caterpillar motion of the dislocation. So the dislocation can move actually only along the Berger's vector. So this is called the glide constraint. And but I wouldn't associate this to any instanton. I'm not sure if there is an instanton. I'm not aware of any instanton, description of this dynamics. Any other question? Okay, then let's get, so all I said so far, it's all known, okay? It's just textbook. You take a textbook and that's all there. Now, what is not in the textbook is when we move to systems which are amorphous. So what are systems that are amorphous? Well, these are systems that do not show a clear lattice structure. So there's no periodic lattice. It's just disordered. And if you just look by eyes at the structure, you will see something like that. So if you want, what people usually claim is that the structure-wise, they are very similar to liquid in the sense that you don't see any long-range order. Now, these are very common. This is one example, cotton candy, but you have many. I mean, that glass over there is one of them. And they don't have long-range order. Of course, this is just a word, but you can actually check it. One way to check it is just you look at the pair correlation function or pair distribution function. What is that? It's very simple. Imagine I'm the tag particle. I do circle around me, and I count how many of you I encounter per circle. Okay, if you are distributed around me in an ordered way, I will find peaks at every lattice spacing between us. If you are distributed randomly like you are right now, if I do that, I will just find a random smooth distribution, which means that there is no order. You are not orderly distributed around me. So this is what you see here. You can see a crystal. The crystal has nice peaks. And then you can see a liquid and the glass, and you don't see any of those peaks when you go to large distance. Now, why you see the first peak is because, of course, you always have the first neighbor, no matter how you're distributed. So short range order is always there because the first 2 or 3 are always making a cage around you. But the next one are not in the class. Now, why this is problematic? This is problematic for 2 reasons. Because if you think about it, 99.9% of the theory of solids is based on this order. Okay, it's based on this order, and also because this order is related to the spontaneous breaking of translation, which is the key in understanding any property of the solid. You think about heat capacity, density of state, thermal conductivity, superconducting instability. All of this is based on the fact that the low energy degrees of freedom are phonons. And phonons have a linear dispersion because they come from Goldstone theorem and blah, blah, blah. So now you see immediately the problem. If I tell you very well, I have something that is rigid, but there's no order. There's no spontaneous symmetry breaking of any symmetry because there's no symmetry to start with. So then what do we do? And one implication is that, as you can see here, many of the predictions of Debye theory, which is the most established theory to describe, let's say, in solid state crystals, failed. So examples is, you see this big peak in the density of state. So the density of state does not follow quadratic Debye law. You see the same kind of peak in the heat capacity and also an upturn at low temperature. That again is a violation of this Debye theory. And here you can see even more clearly, this is the typical textbook thermal conductivity for a crystal. That's a glass. Okay, so they are totally different. This is not the topic of today, but what I want to say is that there are a lot of open questions, and all of these questions are related to the fact that there is no order to build a theory. So we cannot rely on our standard techniques because there's no order. And nevertheless, even if there is no order, of course, you can break a glass. And also, if you deform a glass, you will find that this glass reacts in a plastic way. So here you can see an example. This is a recent review where you can see various types of amorphous systems. That's a metallic glass. That's a colloidal glass that you have just here in the lab. That's a foam. So all of them, once you deform them, say again, sorry? Yes.
I know
Yes, that's correct. So I never talk about rotations. So the reason why I never talk about rotations is that in a crystal, they are slaves to translation. So usually you don't, if you break one, you break the other. Here, I'm always talking about translational order because the theory phonons are based on translational order. The rotation is a different topic. It's true. Let's not talk about rotation for the moment. So the main point that I want to make with this slide is that even amorphous systems show plasticity and break. Okay, and even more, they actually are more plastic than crystals, and they break even easier sometimes. So then the question, it's very clear, is I spent 5 minutes to convince you that, topological defects and defects are the key to explaining these kind of properties in crystals. Now we go to these kind of systems, and the question is, what happened here? Now, to simplify even more the problem, I made this little sketch for this news and views. You can find here. Actually, this is a good place, apart from advertisement, if you want to have a story in 2 pages and not 40 pages. You can just read that. Now, what is the problem? The problem is as follows. So imagine that your crystal is made of chips, and this is your crystal. Now, if I put the defects in your crystal, like these blue chips, it's not very hard. You don't even need torsion or burgers or whatever. You will find the defects very clearly by eye. Or you can do an experiment like, say, I don't know, confocal microscopy. You just look and you see it's there. Okay? Now, what's the problem? The problem is that now you have a glass of chips. Your glass of chips will look like that. Okay? And now, can you tell me if this blue chips here is a defect? Very difficult, right? Because you don't have a configuration to confront with. So you don't have a tool. You don't have some order to compare. And therefore, it's very difficult to say if in this thing there is a defect somewhere. How you even define a defect? Okay? So,
the large scale can still recover some translating variables because it's homogeneous.
no, that's the opposite. So everything is homogeneous, but we're talking. So when I talk about the translation symmetry of a crystal, I'm talking about discrete translation. I'm not talking about global, continuous. So continuous is always broken to discrete. Here, there's no discrete translation that allows me to do anything of that sort. Yeah. So what people did, okay? So various approach. So most of the approach are, let's think about some alternative way of deriving something which looks like a defect. And the typical names are soft spots. And these are associated with plastic events. So first of all, you need to tell me how you define a plastic event now in this system. Okay, so one of the most recognized way to define plastic events is by what is called D square mean. What does D square mean? So D square mean is the following. I do a deformation. If everything follows the deformation in an affine way, all the atoms will move in the same way. So I can make a shear, for example, and all the atoms will move accordingly to a constant matrix. I'm just moving this atom all together. Now, it can happen that some of them do not want to follow this matrix. Okay, this constant deformation. And these are called non-affine motion. So this non-affine motion arrives microscopically because of this disorder. And then what we classify as plastic event is basically through a measure of which kind of particle wants to go farther away from this affine motion. Okay? And again, people in the past try to introduce a lot of method to define soft spots in these systems and to correlate with this plastic event. This is one of them from this paper, and you will see, I mean, in the literature, you will find a lot of this kind of picture with color things superimposing and try to find correlations between them. Okay, so what is bad? Well, there's nothing bad about it. Actually, these things are quite successful, but these are, if you want, phenomenological indicators. So here you can find a paper where you will find a classification of at least 20 of these methods. So these methods kind of work, but these methods are equivalent to this picture. So do you want to know, basically, if this thing is hot? Very well. Put your hands and see if you get burned. Okay, if you get burned, it's hot. That's for sure, okay? But this is a phenomenological, if you want, perspective. Now, on the other side, you can do another thing. If you like to play games, you can just blind yourself, press a button in your machine learning machine, and your machine learning machine will tell you that's a soft spot. Okay? So again, I don't want to take anything away from this method. These are pretty successful, but you can already understand that they will not provide you anything very fundamental. I mean, they will not tell you what is the real reason or what is the real formal object that is behind these things. So on the other side, so the approach that I want to do today is, do we really need to give up on formal concepts? So these formal concepts based on topology and geometry were very successful in crystals. Now, one approach and one very common, belief in the context of amorphous solids is you cannot use them. So just give up and try something else. Now, what I want to try to convince you today is that this is not exact. This is a quite pessimistic view, and you can actually use it. And again, so my goal, if you want, is you take one of your favorite review on topological defects. You see these topological defects appear from liquid crystal to particle physics, and I would also like to add n classes. Okay, so that's my goal for today. Now, in case you fall asleep later, the spoiler is that yes, you can find these topological defects. So there were developments in the last 2 years that propose that you can spot these topological defects even inside this mass. And my goal today with you is to try to give you an overlook of this recent development. Let me also say that these developments are very recent in the last, say, 2 years. So as you will realize very soon, I will propose more questions than answers, okay? So where this started? So this started around 2021 and 2023, where there were 2 different papers trying to propose that indeed we can learn about plasticity and deformations in amorphous systems by using topology. And let me also say, which I think is a nice thing, that China contributed a lot here. Well, I am affiliated to a Chinese university, and as you can see, there are many of famous Chinese scientists in the second paper as well. So this, I think, is an important thing that we are basically the one driving this program now. Now, before I enter in the details of both of these papers, let me explain in a very bullet way what is the idea and what is the novelty. So the novelty is we try not to give up on this topological and geometric concept in favor of adding other phenomenological indicators. So the idea is that indeed it's kind of hopeless to look for topological defects in the structure, but there is a way to look at topological defects in something else. Okay, and this something else, depending on the proposal you like better, is either the dynamical displacement field or the vibrational modes of the system. What are the results? The results so far are that if you use this method, you find a strong correlation between these soft spots and plastic events that people studied in detail in the past, and this new object that I will just define for you in a second. So a quick reminder for those of you who do not work in the field, let me just introduce very quickly 2 simple concepts so that we are all on the same page. Concept number 1 is what is the displacement? So the displacement is very simple, is take your collections of atoms, do a deformations, and see where each atom will move. This will definitely define a vector field for you, and this vector field is called the displacement vector. Okay, so it's represented here, for example, with a green arrow. So now this displacement vector is the base of elasticity theory, because elasticity theory is based on what is called the strain tensor, which is nothing else than the symmetrized derivatives, a linear order of this displacement. Now, what is the problem? The problem is that if you look at this displacement in a real system or in a simulation system, that's what it looks like. Okay, so it's kind of messy and disordered as well. So it seems quite hopeless, but we will see how you can extract information from these configurations. Now, another quick reminder, and here I also put some of the reference that might be useful. Another thing that we can do, we can study the normal modes or the vibrational modes of the system. So how we do it? Well, we do it very simply. Imagine you have the potential of each particle, how they interact. Then as any dynamical system, you can look at the matrix of the second derivatives. This is called the Hessian matrix, or sometimes the dynamical matrix. And this will give you a matrix whose eigenvalues are nothing else than the vibrational frequency, Fm, or the mass of the particles. Yes.
And U is the total potential energy of the system.
Yes, of all the particles that you have. Yes.
It's like a interactive matrix given particles on side are.
Yeah, it's basically, this is a very general concept, is basically the dynamical matrix of your system. Imagine you have a system defined by an interaction of potential. That's what determines basically the vibration around the minima. Yeah. Okay. So now, how does this look like in a glass and in a crystal? So if you look like at the crystals, that's what the eigenvector will look like. If you look it in a glass, that's what it looks like. Okay, and now here you can already grasp a bit the idea. The idea is that you see the crystal, and if you want, actually, these are the phonon modes of the crystals, give you some kind of pattern in the eigenvectors that you don't find in the glass. Okay, so it seems already like you can have some configurations that you can use to define basically something to compare with. And this is basically given by the phonons that are also here. I will go back to this. Now, these are the two concepts. Now I want to do with you, to apply these concepts, okay? And any questions, more questions? No. Okay, so then let's start digging into these developments. And for just standard reason, I just go historically. So the first idea was the following, let's take a glass, whatever it is, and let's look at the displacement field. So as I was telling you before, the displacement field can always be decomposed into two pieces. There is a piece which is called the affine deformations. So these are just the motion that follows the constant matrix. So if you do a shear, you will just basically tilt these things a bit, and each atom will just move by multiplied by this constant matrix that define the deformation that I call lambda there. Now there is a second piece which appears, which is this non-affine deformations, and this comes again because of the disorder, because the atoms are not balanced. Okay, so what happens is that when you do the shear, the atom will move accordingly to the shear, but its position will not be an equilibrium position. So it needs to do an additional displacement to actually find its equilibrium position. And that's what this term is giving you. Okay. Now, what is the idea? Well, the idea is very simple, is that, and to be honest, it's not new. So people knew already, and here you can see a review of modern physics in 2008, that you can still define Burger's vectors, dislocation, etc., in systems which do not have translational order. What is the big difference? The big difference is that if you do these computations in a crystal, you will always find that the Burger's vectors is an integer of the lattice space. So it's quantized, okay? And there's no, you can convince yourself very easily if you just look at the structure that this cannot be other way. Now, what happened here in a disordered system is that this topology, yes?
Yeah, if you regard the displacement as, I think, as you want to calculate the vertical effect using the displacement field.
Yes.
I think the basic assumption is the displacement field can be regarded as a continuous, I think, a similar definition in elasticity.
Yeah, that's very similar, exactly. So the idea is that topological defects will appear in the displacement whenever this deformation is not continuous, so it's singular. But the deformation itself, you will not see anything in the structure. So if you look at the structure, you will not see anything because it's messy. But if you look at the displacement, so you look at how particles deform, you will see that there are singularities in the trajectory of the particle.
You must follow a loop.
Yes.
To define the
Yes.
or charge.
Yes.
But the loop must be continuous.
Yeah, the loop is, so the shape of the loop actually doesn't matter. That's why it's topological. So what it's basically like, I don't know, Gauss law. So you take, you do an integral over a surface or over a loop, and what these things is counting is the total charge inside this loop. So if you have one defect, I put this defect here, I can take this loop, I can take this loop, I can take whatever loop, I will always find the same value because what I'm counting basically the charge of this guy. Okay? So the loop doesn't matter. Of course, then for simplicity, when you want to compute it, you don't take a star loop. You take a circle or you take a square. But that's up to you. So the loop doesn't matter. But your point is correct. So the idea is that instead of looking at the singularity in the structure that you cannot see, you look at the singularity in how this particle moves. So if at a certain point you see that there is some abrupt deviation or something singular in the motion, you will say, oh, there is a defect there.
Yeah.
So I would call this dynamical defect. I don't know how you want to call it. But again, let me stress that this thing was already, people ignore, but I realized actually after we wrote the paper that this was a very well-known concept. So this, in the literature, these were called continuous defects. Continuous, again, because of the absence of translation order, they don't need to be quantized. Okay? But you can still define this order. It's just a continuous number. Okay?
So can you elaborate a little bit more about the affine and affine?
Yes.
Well,
You're not right on the wall. No. Okay. So the idea is the following. So imagine you do a rigid deformation. Okay, so a rigid deformation is just defined by you apply a matrix to your coordinate. And you can convince pretty easily what is the matrix that define your deformation. Let's say, for example, let's imagine you want to do a compression. You need a matrix that is basically the trace, that is the diagonal. And that will just, dilate or compress the system. Now, if you want to do a shear, the shear is actually very similar, you know very well because you work on this, to a graviton. Actually, a graviton is a shear. Okay, so it's a traceless tensor deformation. So it's associated to a matrix which is traceless and the tensor. Okay, so then what happens is that if I apply this matrix to my coordinates, everybody will move accordingly to where you want. For example, if I have a circle, I will squeeze it into an ellipse. Now, this is the rigid deformation. Now, what happens is that because of the system is disorder, once you do this deformation, and you look at where the particle will go to minimize the energy, they will not go accordingly to this rigid deformation. And the reason is that because of this disorder, there is unbalance, if you want, between, for example, your neighbors. And when you move everyone, you will create a situation where to balance this, you have to do an additional deformation to balance. And this is the non-affine deformation. I mean, it would be easier if I can write something, but I can show you how. So if you have a rigid lattice and you do a shear, everybody will follow the shear. Because it's just a rigid transformation. That's it.
So yeah, the assumption is you will be irrespective for you choose L, the BI is conserved.
No, yeah, but this question is different. This question is before you go to B, it's how I define this split.
The slides, right side. If you can define a VI based on the vector field, I think that depends on how you choose L.
No, so the VI, so what this expression is doing is counting the total topological charge, which is VI, inside the loop.
You want to find the possible VI, possible VI.
No, what I'm saying is the following, is that if you don't have defects, so for example, let's go back to what Antonino was saying. If I remove that thing, then it's a constant matrix. Okay, so if I put the UI affine here, I will always find zero. Because I'm doing a constant, I'm integrating a constant in a loop. So I'm always getting zero. So actually that's the reason why I wrote that thing, because I need to stress that in a crystal, if you only have affine deformation and you don't have structural defect, you will always find zero. It's very simple algebra. It's just you're integrating on a loop constant.
Okay. Suppose you can find one quantity defect in your figure.
Yes.
Suppose you can find that defect. Then I put some noise into the system that break the vector direction.
Yes.
Then I think if we increase the amount of the noise, the limit is the field becomes totally random.
No, I think that's exactly the point.
So I think why at the last case you cannot define any BI? Yeah.
No, that's exactly the point. This is topological. So if you add the noise, as far as the noise is continuous, the BI will not change absolutely. Because this object is not sensitive, it's sensitive only to singularities in this vector field. You need a singularity. You can add all the noise you want, you can add all the background you want. If this background is continuous, you will find the same thing. That's exactly why these topological defects are more important than other stuff. Because all these phenomenological indicators or these other non-topological objects, as you said, I add some noise, the value will change. This will not change. So for example, I mean, I don't have here a single example, but you can take, for example, you can take a vortex. Okay, take a vortex and then add on top of the vortex whatever vector field you want. If this vector field is continuous, you will always find pi. Of course, if you do something, if you add some singularities, of course, but how you add a singularity, you need to break something or that's a different thing. But that's exactly the reason, actually, your question is very good, because that's exactly the reason why these objects are better than others. Yeah. Because they are protected. So they are sensitive only to singularity.
That's like I insert many random defect into the system.
If you put a defect, of course, but
But if I put a random field into the system, it likes inject many defects into the system.
I don't think so. If you put a random field and this random field is continuous,
I mean,
we will not have any.
if you put a random field to each arrow,
Mhm.
put a random variable to the arrow. So
But if it's truly random, it's like you just shift the vacuum when. But if you got a non-trivial topological number, it's like you got the one form topological charge. So
I think you cannot.
the excited states would be like you have very little, but you still see the excited state. So the completely random insertion is just like you shift the vacuum. But I think like
Let me make an example. For example, thermal fluctuation in a crystal. You have thermal fluctuations, that's your norm. But thermal fluctuation will not destroy the dislocation. Dislocation is there. So you can add all the noise you want, you can eat it up, and still the dislocation is there. Now, if you do some operations which is breaking or discontinuous, of course you will change the number. But basically, that's exactly the topological definition. The definition of this object is that you cannot change this object with continuous transformation.
but this is still L dependent. Because if you got two
No, again,
inverse vertex.
Again. this is not spotting the defect. This is counting the total topological charge inside the loop.
That
So that's a very important point. So if I do a loop which is like this, I'm just counting how many topological charges there are inside with sign. So then if you want to spot the defects, what you want to do, you want to take this loop small, as small as you can, let's say atomic scale. And then there, if you find 2 pi, you will say, oh, there is a defect. But as he said, it's very correct, is if I put a +1 and a -1 and I do a loop, I find it.
yeah, I know. I know if you integrate the whole system,
Yes.
it will be Kinzawa.
Yes.
I think it
Locally,
break locally.
yes, locally
I
you will find
locally.
something. Yes,
I mean locally.
yes.
I like you insert many defects locally.
Yes. This is the same, like for example, in the
I
original.
suppose they're like 2D melting of this.
Yeah, exactly.
Yeah, you must put many.
You can create pairs. So
That's my question.
yes, you can create pairs. So you will create pairs. Like for example, with thermal excitation, you can create pair, but pair do not change the number of these.
I know. The flow integrity has been done.
Yeah. So this is also a good question. So if you put thermal fluctuations, of course you can. If you are strong enough, you can unbind these defects. You can create pairs, but still you will always create plus and minus. So that's correct. Yeah.
So if I think the fine component of the displacement as a kind of conformal transformation, and then if you think of the finance transformation on hypersurfaces. I mean, I'm trying to.
So geometrically, I think the way to think is that lambda ik is like a constant metric. So then, of course, you will find no defect because the curvature and torsion is 0 by definition.
Yeah, sure. No,
So
what I want to say is that you can also think that the conformal transformation, if you think that the geometry could be confined on these surfaces, the conformal transformation can be seen as involving torsional degrees of freedom because it's orthogonal to the hypersurfaces, so it must be numeric compatible. So in this sense, this would source your topological charge, because this would be naturally connected to the emergence of torsional degrees of freedom that here are interpreted as topological defects.
Yeah, I see your point. But I'm not so sure why that should be because that matrix there is really constant. It's not conformal. It's constant.
I mean, it's
So that is really a constant matrix.
It's a possible.
So it doesn't depend on space.
It's a possible, let's say, realization. Yes.
But you're definitely right. So there is a big understanding of these topological defects in terms of geometry. So you can always think about in that way. So you can think of putting curvature and torsion. And there is this equivalence between the two views. Yeah. is correct. Yeah. Okay, let me show you the result. So the result is the following. So what you see here is the stress as a function of strain. So what does it mean is that we deform the systems and we look at the stress that we produce. And as always, you see that at the beginning, for small deformations, this thing is linear. This is elasticity theory, if you want. And then these things, maybe here it's more evident, but it has drops. Okay, so these drops are basically sudden, irreversible deformation and are called plastic drops. Okay, so what it means is that at that point, the system fails. There's a little failure somewhere, and you lose stress somewhere to reorganize this plastic thing. Okay, so now what you see is that here we compute these Burger vectors. Okay, let me skip the details for the moment, but it's an average thing. So of course, here you have disordered systems, so you always need to take configurations and make averages and things like that to make these things move. But the main point that I want to emphasize is that you see basically every time you see one of these plastic drops, this guy is as a peak. Okay. So here, this is an indication, at least we interpret it as an indication that these kind of mechanisms that are behind these plastic drops are related to the formation or the dynamics of this topological difference that I just described. And you see even more, if you take average, you see that there is a very peaked signal here. So that place there is where the system fails, it's called yielding. Why? Because you keep putting strain, but the stress does not change. So this guy does not react elastically anymore. So when you pass that threshold, you see this guy, this is constant, meaning that there's no reaction whatsoever. Okay, this is like a liquid if you want. It's in the plastic flow. Okay. So this was, if you want, the first sign that was in 2021 that maybe this kind of concept can still be useful even in the context of a glass. And let me say that very recently we posted a preprint where we attempted a more like experimental perspective on this. So what we try to do, we try to measure and to use simulations to correlate different types of objects which are thought to be related to plasticity. So one is this central symmetry. So central symmetry is basically a measure of local order that is telling you basically how ordered are your neighbors around you. Okay, so if you are centrosymmetric, that's basically a situation. So you see that you are very balanced. Okay, so each of the atoms is balancing each other. That's why you are not going to do any non-affine deformations if you want, because everybody is in the position where it should. Now let's imagine I take this one and I move it a bit. Okay, this of course locally will break the local order, and you can see very clearly that now central symmetry, so the symmetry with respect to this central atom, is broken. And you can imagine that now if I deform this guy, of course, this guy has to move a bit more of what it should move to re-equilibrate these situations. So now people in the past discussed that the central symmetry is a good descriptor of which areas of the system want to rearrange more. Okay, which is again very logical. It's a phenomenological, if you want, a description. If locally you are very disordered, of course it will move more. Okay. On the other side, we put this our continuous Burger vector, and at the same time, we also compute what is called the quadrupolar strain, which is another indicator that people use to describe this kind of plastic deformations. And here you can see a little map. The only thing that I want to highlight, also because I'm very late with time, is that you find correlations of these objects at the same place. Okay, so where you find basically large displacement, so a lot of rearrangements, this is the 2D slice, you find also a large Burgers, meaning that the places where this Burgers vector locally it's large are the places that want to rearrange more. There are also the places where this quadrupolar component is strong, and there are also the place where central symmetry is changing most. Of course, as you can see, things become murky because you are going to real systems, so this is the best you can do, but that's already an indication. Now let me continue because I have a lot of things to do. This is maybe a bit more of details about the experiment. For those of you who are experimentalists, you probably will understand much better than me what we did. So this was a colloidal glass systems, and here you can see some of the results. This is we use this technique, which is scanning microbeam small angle X-ray scattering. And you can basically what we did, we borrowed this method, which is a pretty cool method, which is called Fry method, that is used in geomechanics. to reconstruct the strain from just looking at the configurations, okay? And let me say that what we found is that it seems that even at the experimental level, there is a correlation between these different objects, okay? Now, since I'm very late, let me jump to the second proposal. So this was a proposal that appeared 2 years after, and it was led by many people that probably you know, mostly in Beijing. So their idea was slightly different. Their idea was as follows. So I have my glass, it's very disordered. Let me do a normal mode analysis. So let me check the vibrations of the system, okay? So you do a little peep, you see where these vibrations goes, and you can do this normal mode analysis. Of course, from simulations, it's very easy. From experiments, it's a different topic. But for the moment, this is simulations. So they take this matrix, okay? You diagonalize, you get the eigenvectors, and then they say, okay, now I have a vector field. What about I look at vortices in this vector field? And then you can take intuition from either liquid crystals or superfluid, and you can define a vortex. A vortex is just very similar to the object that we defined before, but it's not in terms of the vector, it's in terms of the angle. So what you can do at every position, you have this vector, you track the angle, this is what I call theta, then you take a loop, you compute how the angle change from here to here. If you get a 2 pi, you call it a vortex.
Okay. See here is by local rules.
Okay, so in the simulation, what they did, they choose C as the smallest available loop that they had microscopic. So it was like a 2 by 2, basically. Again, this is important related to his comment, because if you really want to say this is a defect, the loop has to be very small. Because if the loop is big, for example, if I do a loop here, I will find 0, so this will disappear. So if you want to spot the defects, you need to go local. Because again, what this is measuring is not the defect, it's the total topological charge.
If you use local rules, you can also define defect in a random field. So I think this picture lost.
No, so if you take a random field, I guarantee you that you compute that, you will
You
find
can
0.
still calculate the Q using random field.
You will find 0. Unless you have a singularity in the angle somewhere. You can make a complete random field, compute that thing, you will find 0.
Matteo,
So many defects.
No, I mean, if you have defects in this random configuration, of course you will find a defect. I agree.
On many local defects or even a random field based on this definition.
Yeah, look, I'm not sure I understand your question. I mean, that number measure the singularities or the total topological charge.
And you want it to be measured locally.
I want to measure locally because I want to be able to say, here is the defect. Of course, I'm not forced to do that. I can measure it on, here. For example, another thing that I can do is instead of measuring very locally, I can coarse grain a bit and say, okay, in this area, I have large charge. In this area, I have small charge. In this area, I have large charge. But I cannot say that's a defect.
My comment is for local symbols, you have correlation in missing events. But for the medium frequency and high frequency modes, I think that if you calculate using this criteria, based on this criteria, it's actually.
I will show you in a while. But the point is that the high frequency modes are totally irrelevant because plasticity is related to low frequency.
Yeah, for low frequency modes, I think it's okay. But for the medium and high frequency modes, using this,
you are jumping too far.
Yeah, you lost the physical meaning.
You are jumping too far. Be patient. You will arrive now. Now I'm just explaining the method. This is just the method for the moment. That's what they propose.
Okay, a question like, so the number of vortices and the vortices, I mean, the topological defects is changing in terms of external parameters like, I don't know, temperature, external field, kind of things. And second question is how the noise and what kind of noise also enhance these changes.
So here they start from simple things. So this is a 2D system, 0 temperature, nothing external. Okay, so that's the first thing that you want to do. Now, if you go, if you want to go, for example, towards experiment, that is a different story. So back to your question, the total topological charge is conserved. is topologically protected. The number of defects is not at all. Not only that, as Ben was saying, you have one of these fields for frequency. So what you will see in a second is that he's right. If you go a higher frequency, you will see that these numbers they will become millions. You will see a lot of that. Indeed, as we will see in a second, it's not the number of these defects that matters. It's rather the structure, the statistic of these defects. So the number of defects certainly depends on temperature. So to my understanding, nobody ever did a study as a function of temperature. We are actually trying to do that. External field is even less. So for the moment, and you see, this is like 1 year and a half ago. So there's very little about this. So I will show you basically 5 papers and that's all. That's all there is. Okay. So it's a very new field and there are a lot of questions. And I think all your questions are very the point.
Actually, the picture sounds like, because this relates to his question, you really heat it up. Like finally, I think even relates to Lino's question, if you really apply conformal symmetry, then which means you just put all the defects to infinity. Like a completely thermalized, even you can find the steady state almost gapless. You cannot see.
In his case,
Yes, I
look
think
at
this
look
is
at
the-
look at look at
the
this look.
series that is-
Look at this node. It has well-defined key value. It has well-defined key value. It has well-defined key value. I think that's the trick.
The length.
Yeah, I think that's the trick. It means the system has well-defined omega key relation. In the
Of course, because it's low frequency.
I think that's why you can choose C.
Yes, I think it sounds very much like in the inflation scenarios, you started from a homogeneous state, but later if it cools down, you can find the local disordered patch. But at large scale, it's still you can recover the homogeneous.
No, but this analysis is not an analysis at large scale. So plasticity.
Yeah, I know. Exactly, this is like.
So if you do this loop at a large scale, you will find zero. So there's nothing there. Now the questions about temperature and whatever, of course, are very tricky, but that's a different story. I mean, first of all, if you put temperature, you will melt this thing. So it's not even a solid anymore.
Not too much.
And a little temperature, I'm not so sure we do much, to be honest. I mean, we're trying. If you go to low temperature, you don't see much difference. I mean, you will see some thermal noise, but this thermal noise will not do much. So there might be actually what people are after, of course, are these two melting
You can
criteria.
apply, I don't know, some external field of other type. I don't know if electric field, magnetic field.
Yeah, I mean, in colloids you can, of course, but I'm not sure how to do. I mean, I think we are far from doing that. We still don't understand much of your questions on that. Yeah, that's that.
And
Question.
Yes.
For example, when we next model, it's not a proportional PhD. Yeah, we have consider yes. Last time I project you as difference in the last year of my presence of change I calculate.
Yeah, so of course, so in this system they choose the particular potential. I don't remember exactly this exact picture what it was. It was some Lagrangian slide, some 12 and a mixture. Of course, people investigate what you said. So you need to, when I will show you the results, people after check that this is kind of universal and not dependent potential. Now, if I check the potential, of course, this practice will change completely. But the findings that I'm gonna tell you in a second will not change. So we tried at least 3 or 4 potentials and we find similar systems. Now, how universal it is, I don't know. I mean, I cannot make a claim that this is universal. We check in 4 systems, it works. I will show you that we check experimentally and it works. But still, there are many questions from the theory point of view and also from the experimental point of view. Yeah. So, okay, this is the result, their results. So their results, what they claim is that they find the strong correlations between these vortices and these plastic spots. So this is a typical picture that everybody puts. So what is this? So here, this is one configuration, okay? Here is the result of the statistics. Let me first go to one configuration to tell you what they do. So the color that you see here, it's basically the average topological charge that you find in these systems, okay? By averaging a few of these modes. So you take the first 10 moles, say, you average and you compute the average charge locally in the systems, okay? So wherever is red or blue, it means that there are a lot of vortices or anti-vortices. Wherever is green, it means there's nothing happening there, okay? The black is the plastic spot defined with the old method, let's say, d-square mean, etc. Now, this is one spot. Then, of course, what you need to do, statistics. So these are the results of the statistics. So what you can see here, this is the spatial correlations between the vortices and the plastic event, spatial correlation between the minus and the plastic event. So their claim is that, and this is increasing frequency. That's also the question of time. At low frequency, you see there is a strong correlations, local correlations, short range, between the minus and the plastic event, which means that statistically, there is a high probability, a short range, that where you have a plastic event, you have a lot of vortices. Okay? Anti-vortices, sorry, with the minus. Now, as you go up in frequency, you don't see absolutely nothing. And the reason why you don't see absolutely nothing is what already Peng mentioned, that you will get a mass that covers all of this. And actually, this mass is mostly due to the interaction with phonons. I will explain it in a second. Now, on the other side, what they say here is that the plus seems to have no strong correlations, and actually almost a local anti-correlation that becomes even more evident if you do more average. So if you average on the frequency, a low frequency, you find this. You see, there is a strong correlation with the minus and a strong anti-correlation with the plus. Okay? So their claim is that if you use this method, what they find is that these plastic plate spots correlates a lot with the places where you have anti-vortices in this vibrational mode. That's the claim. Okay. Now, this is again, if you have only 10 minutes time, you want to read. This is a 3 pages things that you can read. Just to compare basically these two papers. Now, let me go. Well, okay, I'm already minus 10 minutes. So let me go very quick. So a few other things that happened in the recent years. So first of all, there was a paper literally this year that showed that there is a strong relations between these anti-vortices and this object that are called Ashby inclusions or quadrupoles. So people for a long time believed that this kind of object are responsible for the plastic behavior in the amorphous systems. And this paper claimed that you can actually locate and characterize this object using the method that I just told you. Okay. So for reason of time, I'm not going into the details, but the message is that they found the relation between something that people believed for a long time being the responsible of plasticity and this new object. To be fair, this relation is not so strong as the claim, in my opinion, but okay, that's their claim. Now, going to experiment. This is a paper that we did this year. This is something that you're very familiar with. This is a colloidal two-dimensional system from Peter Keim lab in Germany. So very simply, these are colloidal particles. They interact through magnetic dipole interactions. And well, this is an experimental system, and you can track these systems. And what we did is literally we did the analysis that these people proposed, but in an experimental system. Okay, and what we find, this is the analogous plot, and this is the analogous plot. And what we find is that indeed, even in these systems, which notice is not exactly zero temperature, okay, you still find this correlation. So here you see there are more, these are low frequency, and these are the correlations, and this is the anti-correlation that they find. Of course, we don't find so strong, and we see that it dies pretty easily, but still we see a quite marked correlations at low frequency. This, of course, now is the real system, so you can see units. So these are basically the units where we see these correlations, and this is the same color map plot. Okay, so I'm not going to spend too much more time here. Let me also, regarding to your questions, the interaction potential of this system is completely different from the interaction of the simulations. Okay, so this is a dipole-dipole interactions mediated by magnetic forces. Their interaction was totally different. It was actually purely repulsive. Even they did 2 examples. So we have at least 3 or 4, results where the universality of these findings were confirmed. So I don't think that it depends a lot on the potential of these correlations. Now, of course, there is a question, which is, well, the first question that you will ask is, okay, but most of the systems are 3D. How you do it in 3D? Okay, and here you can see already where the problem comes from. The problem comes from 2 things. One is operational, in the sense that the 3D system, of course, is much more computational difficult to actually handle. But the other problem is that if you notice, all the defects that I discussed so far are kind of two-dimensional objects, like a vortex. What is a vortex in 3D? There's no vortex. Okay. So then what one can try to do? Well, so we did the first approach, which was very cheap. And the idea is basically the idea of cutting the cake in slices. So you can say, okay, I don't know how to do in 3D. Is it enough to do a 2D slice list and then average on this slice and see if we learn something? So one thing that we learned is that if we do this analysis, it seems to be that before and after a plastic event, we find something interesting. We see this big cluster. So these big clusters that you see here in the 3D systems are clustered with high topological charge. Okay, that we color together. So whenever you see a cluster color, it means that you have very big regions around with very high topological charge accordingly to a threshold. What you see is that just before the plastic event, you have a huge number of them. So it looks like these defects want to accumulate somewhere together before this plastic event. And then what happens is that after the plastic event, you will just, boom, destroying this, equilibrate the system, and go back to something like that. Okay, and here there is only one picture, but we actually observed in 5 different plastic events. So our observation here is that it looks like that indeed the dynamics of these defects and these clusters, it's related to these plastic events. Okay, now this was cheap, is the first thing. Why it was cheap? Because one of you could immediately complain, you are talking about two-dimensional slices, but of course you can have a defect that jumps from one slice to another, and you will not be able to track. Now, what is the solution? That we thought, okay, we do a statistic, we do some average, and okay, we will miss one. Doesn't matter because we're doing statistics. So if you have 3 million defects, you lose one, not a big trouble. But of course, from a theory point of view, you can complain, and you should complain. So then, people, well, let me also say, and this is mostly because, I don't want to annoy my colleagues. People tried in the past, in my university, you can recognize maybe some names, to define these defects in 3D granular materials. So here they use a different idea, which is the ideas of these 4 rings and 6 rings, etc., that I explained at the beginning. And they also found that there is a correlation between these rings and these plastic events. Okay, I'm not going to enter into the details because first of all, I don't know enough of the paper, but also time is getting tight. Now, what we did more recently is the following: is now you want to go to 3D. Okay, so to 3D, what do we want to do? Well, I mean, the first idea is that let's be simple and let's find out what is the simplest topological defect that you can have. Now, the simplest defect that you can have is what is called an edge of topological defect. So it's this guy here. It's basically a monopole in particle physics language, if you want. And this is the associated topological charge. Again, the only thing that you need to notice is that now the integral is not on a loop, it's on the surface, because of course you are in 3D, so you need to drop these monopoles. And look, this is basically a cartoonist picture of how you can do something like that. And let me also say that this method is rather simple compared to what I will tell you after. And indeed, we are now applying to experimental data. So we are applying both to 3D granular systems and 3D colloidal systems. And okay, I don't have result to show yet, but that's in progress. And let me say again that even in 3D, using these edge of defects, we find these correlations. Okay, so this is again the 3D analogous of the analysis that I just told you. These are very recent, it's just a preprint. But what you can see is that even these edge og topological defects basically sees these plastic events in 3D. Okay. Now, here there is more. Let me skip it because it's getting late. Let me also say that very recently, actually a few weeks ago, our friends and competitors in Beijing also put a paper, and they are stronger in computation. So what they said is like, no, don't look at points like defects, look at lines. Okay. So what is the problem of the line? Of course, the line, it's what you will like to do, is what is called, it's basically the analogous of the vortex, because the vortex in 3D becomes a vortex line. Okay. So now what is the problem of the lines? The problem of the line is that go tracking it. Okay, it's a computational problem. It's not a theoretical problem. So everybody of us knew that there was a line, but the problem is that it's very difficult to track. So the way they track it, I can explain it to you if you're interested. But basically that's the result. So what you see is that they can start tracking this line. As you can see, I mean, the method is not exactly perfect. There are lines that finishes, line cannot finish, like a vortex line cannot finish in the middle of the system. You have all these things, but still, if you do statistics, basically they also find that these lines relate to the plasticity of the systems, and they also have interesting geometrical properties. And here you can see a view. This is related also, I put it because it's related to our 2D slice thing. You see that if you do a 2D slice, where you see a vortex in the 2D slice, of course, you will track also the line. Because if you have a surface and the vortex line is passing here, where it's passing it, of course, you will find a 2D vortex on the line. Okay? Anyway, this is just a cartoon. I don't show all the results. This is very recent, but they also claim that there is some kind of correlations over there. Last thing, and now because it's getting very late, is at a certain point when we were writing these papers, we sent this paper, I don't remember to which journal, and one referee asked a very good question. And the question of the referee was like, wait a second. I mean, you are taking a class. You are going to the vibrational modes, and you are telling me that the vortex in the vibrational modes capture topological defects that should be in the structure or similar to dislocation. Did you try to take a crystal, put the dislocation, and see if you see something in the vibrational modes? That's a very reasonable question, right? That, of course, we didn't think because it was not fancy enough. It was like, why should I do that? I see the dislocation is there. Why I need to compute the vibrational modes and whatever? But it was a very good exercise, and that's what we did recently. So what you do is, you take a crystal, a real crystal, you can make it. We did an FCC or BCC crystal of high-end or whatever you want. It's pretty easy to do it. Actually, my collaborators are people in the Institute of Mechanics. That's basically their breakfast. And you can put the dislocations there. You can do the normal mode analysis. Now, it's much cleaner because you will not have all this noise and this disorder, whatever. And this is basically, and then the question was, do you see something? So this is the example of the dislocation. So this is the lattice, okay? Here is the dislocation. That is the flip direction. And these are the atoms that are involved in the core of the dislocations, okay, in this crystal. Now, this is the first, and this is the second vibrational mode, lowest frequency allowed by the system. So you can clearly see that if you compute this vortex light, you find exactly an anti-vortex here with charge -1, which is exactly close. Now, the location, it depends on where you take the loop. But if you take the loop a bit smaller or a bit larger, this will move a bit. But you will always find a total -1. So if you surround basically these things, you will always find a -1 here, okay? And here you can see even more clearly, okay? You see that there is this structure like this, like a saddle point, and this is exactly the -1. This is the anti-vortex, okay? So what is the idea? The idea is that indeed, if you have a dislocation in a perfect crystal, you do vibrational modes, you look at the vortices in the low energy mode, you actually see what you're supposed to see. And we did that also for other systems. This is, for example, an inclusion. So an inclusion is just, you take some atoms, you completely remove, and you put something else, which is either more rigid or more soft. And what you see here is the same story. Here it becomes much more complicated, but it's just to show you that, you can do more. But still, you see, well, what you see is that there is always a topological charge associated to this stuff. Now, let me try to wrap up because it's very late. So, I mean, what I want to convince you is that, again, as I said, there are many questions open, but what I want to convince you is that maybe it's a bit too early to give up on the concept of geometry and topology in disordered systems. And there are interesting results in the last 2-3 years that, support the idea that maybe this concept can be useful. Now, we need to see how and to which extent, but that's the challenge. Now, also curiosity, I don't know how many of you are doing condensed matter, but there is a very analogous question in condensed matter that is becoming very hot, which is related to electronic topology. So, topological materials are very popular. Everybody talk about topological insulator and blah, blah, blah. But if you think about how they define topology in those systems, it's strongly based on translational symmetry. Why? Because what you do is you go to wave vector space, you go at the band dispersion of the electrons, and you compute basically topological numbers from there. Example, Berry curvatures, Chern numbers, and whatever. In order to do that, you need to have a well-defined wave vector, and you need to have translational order. Now, what people start to ask, here you can see a review, is what happens if I have a system which is topological and I add disorder, or I have a system which is by itself structurally disordered? Is there any topology there in terms of electron topology? And there, people had a very similar idea. The similar idea is that don't look at the topology in the bands, because the bands, there's no point. You cannot define even a band. What is a band? Look at the topology in real space. And these new objects that they construct are called real space topological markers. And it seems that still you can learn a lot about electronic topology by looking at the real space instead of the wave vector space, which is not well defined. So this, it's reminiscent of exactly what we're doing. We were saying, look, if you look at structure, there's no way you're going to learn anything from geometry and topology because there's no structure. But if you look somewhere else, maybe you can still learn something. Now, open questions, there are infinite open questions. We already discussed many of them, so I will cut short. I will just show the questions here. Of course, the idea of searching, defining, identifying defects in amorphous systems is very old. There are many approaches. And one question which is very important is to try to understand these new definitions. How do they relate to the old approaches? And let me also say one thing which is interesting, because again, there are people in China that are involved with this. There is another definition of defects which is based on geometry. And so the idea is that you can map, again, as we were discussing before, to geometrical quantities. And these geometrical quantities do not really make any reference to the translational order. So whenever I map my elastic problem to a geometry problem, everything is just in terms of geometry. And the people basically push the idea that using these geometric charges, you can still define defects, you can still define two-dimensional melting, etc. You will not see anything in the structure, but it doesn't matter. You can still define these continuous geometric objects. And actually, very recently, there was a paper proving that indeed some of the, well, in simulations, that some of these predictions are actually realized in these systems. So again, if you're interested, I can tell you more. I'm not going to explain the details of this. And I think I'm done. I'm super late. And so thanks a lot for listening.
Thank you very much, Matteo. So I think we have time for a few questions.
Thank you. Very nice talk. Very nice talk. When you hear, you mean vibrational mode. Yeah, I have guess because mechanical response under, I think, under yielding.
Yes.
Yielding is it is close to the linear response.
I think some people would disagree with you.
Yeah. Here, that's the trick. Here, if yielding can be described by vibrational modes. You know vibrational modes.
Linear. Yeah, I agree.
Okay.
I agree.
How about you consider some nonlinear response in the initial energy?
Yes. So
the second order response.
of course you can, and that's actually a very good question. So we are working on extending these kind of theories to nonlinear. And the problem is that, of course, nonlinear physics is much more complicated than linear physics. But what we believe, I don't know if it's true or not yet, is that small plastic drops in the elastic regimes can be well described by linear regime.
Jinwei tried a lot in analyzing the vibrational modes,
yes,
but it is still linear.
It's true. It's linear.
I think maybe another direction is certainly the second order.
Yes. Let me say one thing. So the method that involved the displacement, it's fully nonlinear time evolution. We're not linearizing anything. It's just a displacement. The eigenvectors, I totally agree. Now, the problem is that when you go nonlinear, you don't have anymore an eigenvalue eigenvector problem. So it's difficult to how to define that. People like, for example, Lerner, Buchbinder, and friends are pushing a lot this idea of nonlinear modes. But it becomes complicated now how to define this object in a nonlinear.
Yeah, I think that's another direction. I think maybe tried a lot to analyze it, but I think it is very difficult to find a full story. Why not? Consider another direction. Using the nonlinear part.
Yeah, of course, you know.
The high order part.
I think that one first question is also, when would you expect the linear regime to break down? It's not obvious to answer this question, I think. It's not so easy. But you're definitely right, I mean, as you guys mentioned, there are many open questions.
If you want to explain nonlinear response,
I agree.
You have to use high order terms.
I agree.
That's the basic concept.
I agree, but it's not clear to me when the system becomes nonlinear.
That's your task.
That's what I'm doing.
That's your task.
Because of course, mathematically, I fully agree. Of course, when nonlinear terms, Yeah. I know.
Actually, this also confused me how you constructed this effective theory to describe the system.
But there's basically no effective theory. So, which effective theory?
How do you write out
The Hamiltonian. Well, in these systems, there's really, I mean, you're writing a potential. Like you have the particles and you assume what is the potential between particle I and particle J, and you do a simulation. That's it. There's no, I mean, it's not a Lagrangian or a Hamiltonian. Actually, that's a very good question. That is something.
Well, when you diagonalize the system, then you can claim you've got the normal modes.
Yes.
Yes.
I don't need Hamiltonian. It's just a potential.
Well, but this HIJ, I was thinking it could be a bit too fast, but for me, the HIJ you described is the S matrix in scatters. So,
Well, but then you're thinking about field theory and scattering.
this
is much
location description sounds to me you always have a field theory in mind. You got the background, the continuous background, and then you just apply.
There's nothing continuous here.
No, but still the background regarded as a continuous background. If you talk about lattice gauge theory, there's no real background. You're only lattice, but here you got both lattice and the continuous background.
Yeah, I mean, people tried in the past, of course, you can think of how to do effective description of plasticity in terms of Lagrangian, hydrodynamics and things. There was a lot of work. We did also some, but I think connecting to this real thing is tricky. Because the problem is that in this continuous, effective description, you lose completely the microscopic physics.
Yes.
So you can do something that, will qualitatively follow what you do, but it's difficult to do more. Also, let me say that treating defects at the level of Lagrangian Hamiltonian is tricky. That's why what I didn't mention is that most of the treatment like that use dualities, like particle vortex dualities or extension of particle vortex duality to this thing. So you don't want, when you have a vortex, you don't want to talk about the phase because the phase is singular. So you want to go in the dual description where you talk about the dual object and then the particle itself is the vortex.
Well, but if this location you got, it's a fix somewhere in your lattice system, just treat it as a boundary.
I don't know. Yeah, I see your point, but what we want to understand here is actually the opposite. It's similar to two-dimensional melting. So for us, the degrees of freedom are the defects. So in two-dimensional melting, what people do is you want to talk about the declination or whatever as a gas that interacts with Coulomb interaction. That's basically the theory, the Nobel Prize theory. So you have a gas of defects. Of course, microscopically, it's literally particle for you. And now what you know is that these dislocations interact with something that is Coulomb-like. So they have a log in two dimension is log R interactions. Then you can do some basic thermodynamics consideration, adding potential and stuff. And that's how you find all this DKT transition and stuff. Now, one thing that we're working on is, can you do something like that here? For example, if I give you a picture like saying, I didn't show you the full thing, but imagine you have something like this, okay? Now remove completely the background vector field. I don't want to talk about the vector field anymore. I want to talk about these guys. Now, can I build a description in terms of this guy means the degrees of freedom? So for example, how this guy interacts with this guy? Because now the final thing, and that's also what motivates us here, you see, it seems that plasticity is definitely described by some interaction between these defects. How? What is the dynamics? I have absolutely no idea. So for the moment, nobody studied the dynamics because also Peng was saying, the real plastic thing is the nonlinear dynamics of this object. So then what we want to right now do is, now I want to do, like you said, an effective description in which my degrees of freedom are these guys. And then I need to find out how they interact and how this interaction is basically driving this plastic behavior. That's the idea.
Because once you have it's the well-defined IR model, in principle, you can see dynamically how you spontaneously create this vertex.
Yeah, the idea, I mean, the long-term goal is basically, can we describe plasticity as some kind of topological instability or whatever related to the...
In two-dimensional, here, the two modes, some hybridization with the.
Yes,
defect.
that's correct.
But for 3D system,
Yes.
they
Yes.
go into different parts.
Yes. Yeah.
So I think that's the dimensional reason that you have this different kind of.
Albeit, yeah.
In 3D system.
Yes. Let me say that actually the hybridization with phonons is the reason why when you go to high frequency, things become messy. Because again, the idea, I mean, the original thing is you have elastic degrees of freedom, which are phonon. You put on top of these elastic degrees of freedom some defects. These are basically all these theories of glasses are built this way. You assume some defects and you put these defects on top of the crystal. And then, of course, then the question is how these things interact, how do they evolve and whatever. And it's well known that if you go to high frequency, this mode will interact a lot and will hybridize. And this hybridization makes it very complicated because then how can you distinguish? I mean, what is the definition of the defect itself? It's very tricky. Because the moment it will hybridize with the phonons, you will see, for example, this story, well, maybe you're not familiar with this story, but this story is very popular in the concept of these quasi-localized modes. Okay? So many people believe that, all the responsible in these classes of these anomalies is you have some modes that are quasi-localized because there is disorder. And actually, this is a very old exercise. You take a crystal, remove one atom, and put one atom which is 10 times heavier. What will happen in the vibration? Well, definitely you will have a mode localized on these things that will not care about the rest because this guy is 10 times larger. So if this guy is oscillating, the rest is completely irrelevant. So you will find the localized mode there. Now, what is the problem? The problem is that these quasi-localized modes are very easy to see at low frequency where things are decoupled. But when you go to higher frequency, you will see that there's nothing localized. Why? Because these guys are interacting with the phonons, so they are carrying phonons with them. They become delocalized. And that is very difficult how you say, here you are, the defects. And people are trying with nonlinear methods, with a lot of stuff to try to de-hybridize these modes. But it's a very complicated question.
In China, there are many scientists who study nonlinear statistics. They are real experts. For example, Liang and Xiaosong Qin. I think you will discuss them with, I think. Okay.
Yeah, the nonlinear problem is interesting. The nonlinear, I think. But I would like first to understand the linear one well.
Yeah, they are excellent.
Before going on linear. But
So, one question. Are there any questions?
One question. Yes. So I wonder, thank you for talking first, and I wonder why it's negative in a lot of units.
Okay.
Because I think from this picture, I think what matters most is the direction of this positive vortex.
Okay, let me explain one thing. That's a good question. So the red is the positive, the blue is the negative. The red, that the direction is not the topological charge, it's called the chirality of the defect. So both these and these have topological charge +1, even if you see this guy rotating in one way and this guy rotating in the other way. Now, what these people claim, and actually, let me say I agree with you, I don't think it's so clear. Indeed, in many of our findings, we don't see such a clear distinction between positive and negative. But they claim that negative is more important, at least in their systems. The reason they give, it's very hand wavy. It's look at these things. If you look at these things, you see here, it looks pretty stable. The -1 is exactly saddle point. So you see, it's basically very unstable directions everywhere. So their claim is, well, their explanation for their finding that the negative correlates more with plasticity than the plus is that this is kind of a stable place in terms of displacement. While this one, you move it a bit and you will just fly away. But it's very unwavy. I mean, there's no...
This negative charge is not the reason, because from physics, I think maybe it's because in masses we have different clusters, and these clusters, they move in a positive charge way. And the direction of these motions, if they are in different directions, then this is a defect.
Yeah.
Or it's like
Yeah, I understand what you're saying. So actually, let me rephrase what you just said, and I agree. So if you think about these things, that's exactly what you're saying. This is actually a quadrupolar structure device. You can see it very clearly by height. So that's exactly what you're saying. There are basically, it's a kind of frustrated region where somewhere you want to move in this side and somewhere you want to move in this side. This guy here is not very clear. And actually, there is also another thing which some of you should have noticed and complain maybe after, which is something that I complain with them and still they agree with me. But so look at this. Look at the crystal. Do you notice anything? Isn't this full of vortices and anti-vortices? This is a perfect crystal. Where do they come from? I told you all the time that these vortices and anti-vortices are plasticity. What plasticity? It's a perfect crystal. So what are these? These are phonon modes. You take two transverse phonon, one on top of each other, you will find a perfect grid of vortices and anti-vortices. This is the wavelength of the phonon.
Minus one, negative.
So that's what I was saying at a certain point. I say that their claim, and they know this claim. Yes, this is minus, plus, plus, minus, plus, plus, minus, plus.
Yeah, plus
Yes.
one and minus one.
Yes,
But
exactly.
they are always
Exactly.
coupled and
Yes.
total is.
So what is the point? The point is that this distance is the wavelength. If you go at low frequency, which one?
Here, that's a minus one, positive one, but here, you can see here is asymmetric.
Yes.
I think the asymmetric feature, I
Yes.
think is also very important.
That's a very good point. Indeed, you can see it. Well, I don't have slides, but that's important. So that actually they know it. They didn't write it explicitly in the paper. There is some little sentence somewhere, but it's well known that phonons give this kind of object. So the claim then is that you need a way, and actually for me it's a good thing because I know that the phonon is giving me an order structure, even in a glass. This order structure comes from the phonon mode in the glass at low frequency. So then, where you find the plasticity is how you destroy this order in the vibrational modes at low frequency. That's the plasticity. So if you see a vortex there, doesn't mean that's plastic. What you need to look at, that's what I was actually telling to Antonino at the beginning when he asked, is you should look at the structure of these guys. And why you would say, but okay, but you just tell me you don't look at the structure, now you want to look at the structure?
Here the dynamic structure is very asymmetric.
Yeah, because you see, so the point is, even in a glass, the phonons will give me a structure in the vibrational mode. And that's the trick, because once you give me a structure, then I can define the defect in the structure. But I need to be careful because the defect doesn't mean vortex.
And that's the harmonization part.
That's actually why, okay, now I'm selling my part. I believe that the burgers is better. Because the burgers, if you compute the burgers of a perfect vortex, you can do it analytically, you find zero, completely zero. So one thing that actually we are trying to work, even using this, fancy machine learning and stuff like this, is there a way to filter out the defects that are not defects? And that's also going back to my titles. Are all the defects equals? No, they are not. Not all these vortices are plastic. So if you listen to, if you read these papers or if you listen to talks, and these people will tell you the vortex is plastic, it's wrong.
If the phonon structure is perfect, then the defect cannot extend in the omega space.
Yes.
Yeah, okay. That's why if the vector field is asymmetric in the
Yes. So here you see, this is an extreme example, okay? So here you see there are perfect phonons. If you have a good eye, also here there are the phonons behind this thing.
Yeah.
Behind these things, they are fully distorted.
Can you do Jamie's recent work? Jamie's unpublished work. The extension in omega space.
In 3D.
Yeah, here.
Yes.
If they are perfect phonons, then you can only find the unconnected, disconnected defect.
Yeah.
But if here, this mode has a symmetric part, in the displacement in the vector field, then I think the defect can extend in the omega space, then form a chain. Yeah.
Yeah, I think I agree. So if you want to push this, the idea is that there is still a big problem, which is you have to filter out which of these vortices has nothing to do with plasticity. And of course, this question becomes very hard if you go to high frequency. But in low frequency, you should be able to do that. Also, the point is that the distance between these things, remember, is inverse to the frequency. So if you go at low frequency, you will have very few of these vortices which are due to phonons. When you go to high frequency, that's what Ben was saying. If you look at their paper, at high frequency, you will see nothing.
Sorry, the orbit of the defects that are not equal to the other one, when for orbit, I really say, I mean, it's the flow orthogonal to the vortices. Do they have some special dynamics to end up somewhere? Do they have some particular feature?
So far, nobody studied the dynamics yet. It's something that we want to do. I have no idea. So for the moment, all is done. So people have, I mean, to make a summary, if you want, of the situation in the last 3 years. So people try to define different type of defects from the modes or from the displacement. Either vortices, burgers, or lines, or edge-hog, or whatever you want. My belief is that actually at the end of the day, probably will not matter too much which kind of defects you will actually define.
Defects that are connected to stress energy, I mean, these are somehow protected topologically in the sense that you should.
The total charge is protected. That's you to be careful.
But this is the point that I still have to understand, because we talk about the total charge.
What is protected is the total topological charge.
Okay.
That's conserved.
But if you think in geometric terms, the topology itself of a manifold.
Yeah, but that's a global thing. It's like Euler number or whatever. This is the total thing.
Yeah.
You integrate on the full manifold.
Because I mean, these are defined.
It's like, like the number of holes or, the Euler characteristics, these kind of things. Like Gaussian curvature, you integrate it over, this kind of stuff.
Yeah, but you can change.
It's not local. Local is not conserved.
Well, but I mean, if you think in terms of a manifold, you can change the manifold topology locally, and this will refer to be a global in the sense that it's no matter.
But you cannot do that without in a continuous way.
No, you can do that through
You need to break
the injection of a noise.
I don't think so.
Well,
you cannot create a hole in a system by noise.
I mean, it's in a
cup.
I mean, the Ricci flow, which is the one that was studied by Perelman to prove the Poincare conjecture, exactly uses a thermal flow.
But you will create always pairs. Always pair. I mean, the total number, you can create defects, but you cannot create a total net topological charge.
But the point is that
so locally you can create a lot of things. Yes.
You go out of equilibrium. That's the point. You need to go out of equilibrium.
Okay, so then if you go out of equilibrium, yeah, that's, I don't know.
Well, then it's a dynamical question.
Yeah.
But
it's even more dynamical. It's not linear. So you're saying that in the nonlinear evolution, the topological charge will not be conserved anymore?
But
It's not.
actually, I think I have a similar question regarding this. So if you from the beginning, like you said, you insert this distortion of your lattice like by hand, then like it serves as a different boundary condition, right? You get different normal modes. So if you think it in the field theory way, it sounds like you can mix up some state and you re-diagnose it, so you get different modes. But in principle, then in this way, it's possible that you get a totally chaotic system that you cannot diagnose. I think that's the one extreme.
Why you cannot analyze?
You have done. The states mix up completely.
I can take an FYK model, it's totally random.
It's one thing. That's actually one reason I don't like low dimension. Yeah, I mean, so in principle, you can construct chaotic system,
Mhm.
even in the equilibrium.
But you see, going back, I think to that question, I think if you go out of equilibrium, then you need to put an external source or something. Like for example, you take a superfluid, you rotate. If you rotate a superfluid, of course you create vortices. But these basically you are transferring the angular momentum of the rotations to the winding of the vortex.
If you put an external source for these wooden ends, for sure.
But otherwise, how can you be out of equilibrium? I mean, if you don't put an external force, the system will go to equilibrium.
Yeah. No, that's external force for sure.
So maybe my statement is that the total topological charge cannot change, of course, if you don't put external deformation.
That's why I was asking you before about
How did you react?
the
Yeah, I don't
parameters,
know.
how you can change because I was thinking exactly.
I don't know. So all actually, let me say one thing I didn't say. All these things are quasi-static deformation. You never do. No.
Yeah, no, it's clear. That's clear.
So if you do that, no idea.
And let me ask you a last question. So in this analogy between geometry
Yes.
and I would say at the end of the day, I mean, it's any kind of gravitational theory is a topological quantum field theory default. Okay, so then let's say in this analogy between then extended topological quantum field theory and this presenting. What is the internal symmetry group? In the sense that for gravity, the internal symmetry group is Lorentz, is locally Lorentz. So here is rotation.
I think it's Euclidean. Euclidean iso.
Euclidean rotation.
I think it's.
Or
no, it's definitely not Lorentz because these are not relativistic.
Yeah, sure. It's not Lorentz, but is
actually that's also one thing. When I talk about gravity or geometry, only spatial.
Yeah, sure.
So that's only spatial. So I think the symmetries there are literally iso. I think it should be some Euclidean manifold.
Maybe it goes like the symmetry of the base manifold where these things are defined, or it goes like an internal symmetry of the system, so these are n constituents, and then we may have some orthogonal or symmetry like V, no?
So the idea that you think about, for example, the way you do elasticity in this way, you need to think of a manifold embedded in a space-time. And then you define a reference metric, which is basically the equilibrium position of this atom. And then you have this dynamical matrix embedded in this manifold. And that's represented the formation of the system. So the strain tensor gets mapped to this metric, which is the difference between the actual metric and the reference metric. And then you can construct this. For example, elasticity theory can be written in terms of these geometric things. Now it's also clear is that group? I think it's some Euclidean groups, but now you got me unprepared. I don't know. Yeah.
Because I mean, this is relevant for something that I'm gonna talk to later, which is something that I mean I've been working with Matteo, and there's also a way to map this with some algorithm, quantum computational algorithm to do machine learning. Because basically the system will be described by a similar configuration that should capture the topology at the level of the connectivity of the dual graph.
It's very similar.
And I think, I mean, this could be a way to look at the structure.
That is similar probably to the topology of the displacement. Because the connectivity of the graph is basically how these things display. It looks very similar. So that was similar to our idea. Our idea was, instead of looking at the structure, can I define basically the defects in the dynamical evolution? So if you have something which is order and nothing, whatever, you will expect that these things will follow a continuous evolution. If at a certain point this is a jump, it means that there is a defect there.
Yeah,
that was our idea. And we were like just computing this, but indeed, if you can map it to some kind of that's actually something that they do a lot in these classes. So what you do this Voronoi construction.
Voronoi, exactly. The same is what was asked by
So if you do the Voronoi construction, then basically the defects would be the defects in the displacement would be exactly what you're saying. It means that in the Voronoi, the evolution of this Voronoi graph, you will have some breaking or some singularities or something.
Exactly.
And then this is also related to the fact that these things will be related to irreversible deformation, because if you break something, you cannot go back. If it's a continuous deformation, you can deform it as much as you want, I can go back.
Exactly.
If you have a singularity in the deformation, how I go back?
Yeah, no, exactly.
Yeah, that's very interesting. Yeah.
Yeah, actually, I'm thinking of.
I think we have to leave because in a while there is
Yeah,
last
the
question.
We can discuss more.
yeah, I'm thinking of similar questions, but need about more techniques.
Okay.
I'm curious about your Heising matrix. Your Heising
Yeah.
matrix that because it seems to me it's not. It seems not exactly the definition of Heising in geometry, but it seems it is similar to the definition of the limit of tensor. So I think maybe it's not
Yes, it
use this Heising by current tensor and maybe related to this or using the portion of the charge as the coordinate in the.
Yeah, so actually, maybe I can tell you one thing, and then we can close.
Yeah, please.
In the context of this geometry, plasticity is related to the fact that the reference geometry is actually dynamical itself.
Yeah.
So it has some additional dynamics that come from basically the fact that, and there is also a very beautiful description of plasticity in terms of hydrodynamics that I didn't talk at all. But yeah, I think there are many ways to find it. And also, one of my dreams would be also find a field theory for plasticity. Many people.
But then it's super nonlinear. I guess it's like you turn on.
That's life. That's life. Life is non linear.
It needs like you turn on dynamical gravity for.
Yeah.
But the nonlinear is
Yeah.
linear is to multiple linear.
But it's unavoidable.
Yeah, such as work.
I'm thinking using
Yeah,
or some
such as work is related to that.
It's not linear. Yeah.
very nice problem.
Yeah, great. Okay, so here we. Bye to everyone.
Yeah, what I like is that there is a lot of mechanism